Oh, okay, 1 minute. They cannot hear you online. Hello, can you hear me clear now? It's okay. I'm still listening. I guess we continue. So the problem with the notion before is that images are very large, usually. They have a lot of pixels. So if you imagine a total image that is 32 by 32 by 3. So really it's the element then we need to these are channels. And then those by in the end. So I have physical pixel and then the hyperphysical pixel. You have three things and this is over by 4, but really number to 150,000 and now that you can see a lot of things. So probably pixels that they lots of predicting power around people. So we need to come up with stations. Yeah. So for here, we'll look at the institution page and then we'll run the input there and convert it to CPU. So if you have a ratio but then already we have three separate channels, each representing the value of the relation itself. They represent an integer image open, or then there's so that in the next then I also yeah, a problem. So here we have the then I'll just start this now and the next one will be what we can there for proceeding to this one. And then we'll have so this what we mean by different perspectives is the model these features will be And then finally, we have the classification task. This is okay. Yeah, so the classification layer at the end is basically similar to the neural network layers that we have described in the last session. They would just be a normal feed-forward network, and then the output would be the number of classifications or objects that you want to detect. So the final layer, the number of out nodes would be the number of objects that you want to detect. Okay, so as I described, there are three main parts. Can also be just classified into two. Basically, the input layer can also be considered a feature extraction layer. So the input layer here will just process the incoming image, and then the feature extraction layer will do most of the processing, which also has the convolutional layer, which is this one, convolution. So it consists of three main parts: the convolution itself, and then an activation function. ReLU, if you remember from last time, the last session, ReLU is an activation function, which basically eliminates all the negative values, turns them to 0, and then anything positive will remain the same. And then you have also a pooling layer. So I'll go into details for these layers in the upcoming slides. Okay, so this is the feature extraction layer that I just described. Usually it's just like this: convolution first, one convolution layer, and then ReLU, the activation function, and then a pooling layer. So it's also like the CRP, and so on. You can add more, or you can play around the architecture, but this is the basic architecture for a convolutional neural network. So the convolutional layer does the convolution, which I'll describe in the upcoming slide. And then you have ReLU, which is just the activation function, as I described. And then you have the pooling layer, which basically reduces the dimension so that it's easier to process. I'll also explain in details later. And then finally, you have the classification layers, which is just the same as feed-forward networks. Just classifies based on the features detected. So the only thing that is different for the convolutional neural network compared to the feed-forward neural network is this feature extraction part. After the feature extraction part, the classification layer is exactly the same as we did previously in the last session. So let's start with the math part. And this is the convolution itself. So the convolution is an operation that requires something called a kernel. So this is the kernel. It's just a matrix that we define. And this kernel is also trained. So this kernel, the values in this kernel will change throughout the training. So this is what you're training when you're training a convolutional neural network, the values in this kernel. The operation is simple. This kernel will pass by the large image. So imagine this larger matrix in blue, or this larger matrix in gray, is the image itself. And then we have our kernel that has a specific size. In this case, is 3 by 3. So what we'll do is we'll move this kernel from the start of the image, maybe from the top left. So at the beginning, it will target this square, for example, which is this square. And then it will do the operation, which is just multiply each of the values with the one that is overlapping. So in this case, 1 multiplied by 1, 0 multiplied by 0, 1 multiplied by 0, and so on. And then once you have all these multiplications, you add all of them. You get the sum of these multiplications. This is basically the convolution operation. And then the kernel moves on to the next part and so on until it covers the whole image and keeps shifting. Each time it shifts, it computes the multiplication for the dot product basically between the two matrices. And then it adds the sum of all of these numbers. And so you can try this. This is an example. The output should be 4. So this is 1 multiplied by 1, so it's just 1. Both of these are 0. This is 0. Okay, this is 1 by 1. It's 1. And then we also have here one by one. So the total is 4. Everything else becomes 0. Okay. There are some other examples here. But I want to make sure that you guys understand first. Does anyone have any questions, either online or physical, for this convolution operation? Oh, completely. Okay. The second concept that you need to get is the padding. So when doing convolution just now, we didn't have any padding. This previous slide, there was no padding. Padding essentially means adding a layer of zeros to the outside of the image, to the pixels. I can show you an example here. So adding these zeros, just the outline, a border basically of zeros around the image. This is called padding. And you need to do this for 2 reasons, or you can choose to do this for 2 reasons, all up to you when designing the model. The first problem is that every time you do convolution and do polling, the size will reduce, the size of the image, the dimension of the image. So what you can do is add padding when you're doing the convolution operation, so that when it reduces, you have the same size of the image. And then the second reason would be to preserve the information at the edges. So essentially, the matrix, the kernel matrix that's going around, only passes by the edge the first time. So it passes by this edge and then it goes on. Compared to the pixels in the middle that have multiple kernels pass by them, the pixels at the edge of the image are not processed as much. So when you add padding, you kind of push the pixels that were on the edge to the middle a bit, because now we have an extra border. So the one that is not getting processed as much are just 0 values, so they don't affect as much. And then the pixels that were at the edge are now getting more exposure. Okay. So this is an example of the padding operation. There's also something called the stride. So the stride is basically how much the kernel moves after it does the operation. So in this case, stride equals 2 means it will not just move 1 pixel, the kernel to the right, for example, it will move two pixels. So if you see, it's here, and then moves on to this area. So the area that it moves is 2 pixels. If stride was equal to 1, it would have just been at this area instead. Okay. So these are just some parameters that you can play around with when you're designing the model. You can change the stride, see how it affects the detection and so on. So it's important to know the size of the image after you do the convolution process. So there's this equation that helps you decide, or you can also just do it manually and see what is the output, but it's much easier to use this equation. So let's define the variables here. I is the size of the image. Usually the image is in a square shape, so the size would just be one of the edges, either the width or the height. So let's say I have a 32 by 32 image, so I would be 32. And then you have B, which is the padding. How many pixels of padding did you add? 0, 1, 2, and so on. And you have the kernel size. So if you have a 3 by 3 kernel, this would be 3. The value would be 3. Or 2 by 2, and so on. You also have stride, how much the kernel moves. F is the number of convolution filters used. So you have the choice to not use just one kernel. You can use multiple kernels. And what this does is it increases the depth, basically, of the dimension. So F is how many kernels you've used during the convolution process. You can use just one kernel. You can have multiple kernels. They will all do the same process, go around the image, doing the convolution operation one by one. And then you have the output size. So basically, you use this equation to get the O, which is the output size, and then the output, the tensor size. Tensor is just the way that either TensorFlow or PyTorch holds the dimensional data, just an array basically. And then the output, multiply the output, and then F is the number of kernels because this decides the depth. The number of kernels are always the depth. Is this easy to understand? Is it okay? Is everyone following up? Okay. Any questions from online? Okay. Let's continue. Okay. So this is just an example. As I described, let's say the input of the image is 6 by 6 by 3. Okay. And then you have multiple filters. You have filter 1, filter 2, each of which are 3 by 3 by 3. Okay. And then the output will be 4 by 4. And then since we have two kernels, we have two filters. We've used two filters or two kernels. Then the depth is 2. So this is basically the operation. So as I said, the number of filters or the number of kernels, in this case, two filters. This is the first filter, the second filter. Decide the depth of the output. And overall, in the convolution operation, the size, the output size, shrinks, and like the 2D form, the image itself shrinks, but the depth increases. Okay, so this is what happens every time you go through a convolutional layer. This is what happens, and you can try to maintain the same like 2D size of the image by adding padding. So this way, the 2D size is maintained, but then the depth keeps increasing. Okay. So this is the activation function, loop. We've already explained a lot in the previous session, but I'll just explain again. What it basically does is just removes all the negative values, turns them to 0. So anything negative, anything before the 0 on this graph, it just becomes 0. And then anything positive is not affected. It just maintains the same value. So after each convolution operation, usually they follow with a ReLU activation function or ReLU layer. Okay, now we go into pooling. Pooling is basically a method to reduce the number of parameters or computation that we require during the network processing. So what it does is just reduces the dimension, the 2D dimension of the image, even, I mean, way more than the convolution operation already does. So all it does is it chooses some pixel values, depends on the size of the filter. So this is, for example, 2 by 2. And this is using max pooling. So the commonly used one is max pooling, which just takes the maximum value. So in this matrix, you have 1, 1, 5, and 6. Okay. So you just take the maximum value, which is 6. So in this new matrix, the value will be 6. And so on. It will do the same for each of these matrices. The size of this matrix depends, we can set the size depending on the pooling filter that we set. We can also set the stripe similar to the convolution operation. So all this does is reduces the number of pixels that we have to process, and it chooses the maximum value because it's trying to get all of the features in the image, and usually the maximum value is the brightest or most significant pixel in this area. Okay. Any questions about pooling? Okay, no questions. Okay, so finally, the final layer is the classification layer. And as I said, this is just a normal neural network. It doesn't have anything to do with convolution. This is just the classification layer at the end of any neural network. Basically, usually has just a fully connected network, or just a normal linear network. And then has the output layer. The output layer has the number of classes or number of objects that you detect. so. So all the processing, the image processing happens at the feature extraction layers. This classification layer can remain the same, usually remains the same for all models, unless you have some other type of data. So let's say you want to process an image, and then you also have some like numerical data. The image would be processed through the feature extraction layer. And then you would have another network, a normal neural network that processes the numerical data. And then you would merge the output. The operation is called concatenation. Just adds them both into one layer. And then you can pass them to the final classification layers. So now you have both image data and also numerical data going into the classification layer at the end. Each of them will be processed for their features. You get the most important features for the image. You also get the most important features for the numerical data, and then you pass them both to the classification layers at the end, so that you can output the detected or the class study. Okay. Okay, let's start our first hands-on session. So the first thing that I want you to do before we look into any code, I want you to collect your own data set of images. So I want you to go to Google and then search for, let's say, sushi, for example. It's up to you. You can select any classes that you want. For this case, we're doing sushi and also nasi lemak. Okay. So just go to Google. You can manually download the images, put them in one folder, or you can use an extension. I'm using this ImageEye extension. It just gets all the images in this web page. But also filter them by size. We want the highest quality images, so select the largest size. And then you can basically select all and download all the images. So download the images for the sushi, and then download the images for nasi lemak, and put them both in one folder. I'll give you around 10 minutes, maybe. The extension, okay. So the extension that I have is called ImageEye. You can just go to Chrome extensions. I think it's called ImageEye extension. Yeah, this one. And just add it to your browser.
Yeah.
Okay. Who still doesn't have the images? Everyone has the images downloaded, right? Okay, let's continue. So the next thing that we have to do after we get our images is to label these images. So we'll go to a website called RoboFlow. So you can create an account, go to RoboFlow, create an account, and then we'll create a new project. But I'll just wait for you guys to reach this. If you're prompted, choose the free version, the community version, I think it's called, while creating your account. Okay, you guys have your accounts. Let's continue. So next, you're just gonna start a new project. Okay, press on new project, and you will see this screen. So you can name the project. You can name it, for example, resistors or something. Okay. This annotation group means what like overall general group does this belong to. This is just for when other users search for data sets, they can find your data set. So here you can just type food, for example, just the general overall label. The license is okay, you can ignore for now. Okay, as you can see, there are multiple tasks that you can do. The simplest one or the easiest one is classification. So we will choose classification for today, which means just labeling the entire image with one label. So for object detection, for example, you're not just detecting what this object is, you're also detecting where this object is on the image. For classification, it's just the whole image. You just, okay. And then there's also segmentation, which is harder than object detection, which is just not the regular bounding box. You also do a mask around the object itself. For now, we'll just select classification, and then you can press on create public project. So once you create the project, you can now drag all the images that you've downloaded, drag them into this. So you can see them here. I'll also drag the images that I have. Okay, these are all the images. I just select them all, and then drag them. Okay. Once you have the images here, which I think for some of you, if you're using UTM Wi-Fi, it might take some time. but then just click save and continue. I'll wait a bit. Did your images load already, or still uploading? I will upload it already. Okay. Nice. So this is the labeling section. So if you're working in a team, you can choose to assign multiple people to do the labeling. But if you're just by yourself, you can just select label myself. Or if you have a team, you can select label by team. They also have some paid features which auto labels if they already recognize the objects. But for now, we just label ourselves. So we'll show you this screen where you have the images that you're currently annotating. These are the images that we still have to annotate. They will have some unassigned images here if you have multiple people, so you can assign some people to do some images, label some images, but since we're just labeling everything ourselves, so everything's already. And then once you finish annotating, they will move on to the dataset. They will become your dataset. So let's click on start annotating. And let's see the images. Okay. So once you click start annotating, you will have an interface like this where you can type in the label. For example, this we already know is Nasilama. Usually you wouldn't want to have images that look like weird drawings if you're trying to detect actual food, but for this example, it's okay. And you can just press on save, select this Nasilama, and so this is already labeled. You can press on next, or you can press on this to move on to the next. Oh, this ends the labeling, so don't press on this. Press on the arrow. Yeah. So this is sushi, although it also looks weird, but it's okay. Press enter, make sure it's selected, and then go to the next. You can also use your keyboard. It's faster if you use your keyboard. So up and down to select the label, and then left and right to move on to the next image. So go through all the images that you've downloaded, label each of them, either Nasilama or sushi. Make sure everything is labeled. And then after you're done, press on this check mark, add images to the dataset. Depending on the number of images you have, this might take some time. If you're already done with the annotation part, make sure that you select this split images between training, validation, and testing. And then you can leave these as they are, 70, 20, 10. It's okay. And then they should appear here at the dataset part. And then you should now have some images in this dataset tab at the left. Then you can review the annotations and so on. If you click on them, they should already be annotated. How many of you are already done with the labeling? If you're done, maybe you can raise your hand. Good. Nice. We'll wait 5 minutes more. Then. Okay, let's continue. So after you have your data set, make sure that in this data set tab, you have the images that you have, the number of images that you have. Should be like this. You can browse the images that you've added. And then once you go to versions, you can create a new version of this data set. So this version just means that we're choosing the images that will be in the data set. We'll do some augmentation steps. We'll prepare this data set so that it can be used directly to train a model. Okay. So you have some choices. The images are okay already. It's okay. The train test split, just make sure that some of the images are in training, some are in validation, and some are in testing. If you don't have some in each, you can click on rebalance and then rebalance this ratios. Okay, we'll move on to pre-processing. Usually they have these two options. Auto-orient means it just makes sure that the image is oriented correctly for the model. And then resize so that all of the images are the same size. In this case, 640 by 640. If you want to change the size to something else, then you can edit the size here. You just press edit and then specify the size. This is important because we want all of the images to be the same size so that later on when we're designing our convolutional network, the input size for the image will use this value. Okay. And then press on continue. Next is augmentation. So augmentation just tries to create more images from the current images that you have by doing some modifications to the images. And therefore, these other modified image versions are the ones that are created. So I'll show you what I mean. So let's say flipping the images. So it will take some of the images in your data set and then flip it. You can choose whether to flip it horizontally or vertically. For now, we can just choose horizontally. You can also flip it vertically. So this improves the performance of the model, because if the model sees these images when they're flipped and so on, means that later on when you have your camera and you're trying to go around to detect something, the model has seen this object flipped around, has seen in all different conditions, and therefore the accuracy will be higher. So we want to add some flipping. We also want to add cropping so that if it's a bit smaller, a bit larger, doesn't matter for the model. Just apply it directly. And then we also want to play with brightness. So this is one of the most important things, I mean, for model performance. Usually, one of the most critical aspects that affect the performance is changes in the lighting for the room and so on that you're using the model. If the lighting is a bit different, usually the model's performance drops. So you can avoid this. You can avoid this drop in performance by introducing these changes in brightness in the images itself and the training before the model has to experience them after the training. So if the model has already seen these variations, then it will perform better when it sees the same variations again in the actual environments. You can continue adding more. There's blur. Blur is also okay in case suddenly the camera that you're using loses focus or something and the image becomes blurry. All of these are nice. Just don't choose ones that affect the detection. For example, grayscale. This might be good if you're maybe using X-ray images, so you don't care about the color. Grayscale is okay. But if your features of the thing that you're trying to detect has a color, and you choose this grayscale image, then you're gonna reduce the performance of the model. So don't choose this for now. I think that's okay. You can just add these 4. If you want to add more and experiment later, you can create new versions of the data set. So just press continue. This is the good thing about RoboFlow. So basically, the augmentations that we've selected will multiply the size of our data set by 3. So now you've only labeled, I think, around 100 images if you chose like 50 for Sushi and Nasirama. But then RoboFlow will duplicate this, will make it 3 times the amount of the images that you labeled. So now your model has more data to train on. You can also select 2 times, or if you're subscribed to their model, you can select up to 15 times. But three is okay, right? Okay, and then just press create. So it will create the data set. And once the data set is created, we can now use it to train the model. Okay, so now this is the data set. If we press download, you have options. You can either download it as like folder structure, or if you're using a specific model, you can select the format for this model. Make sure to uncheck this. We do not want to train on the RoboFlow platform itself. We want to train our own model using our own network. So uncheck this. Don't select this. And then we will also select show download code. So we don't want to have the data set locally and then have to upload every time to Google Colab. So when we want to train, we'll just get the code, and then this code, when we run it in Google Colab, it will automatically fetch the data set from RoboFlow. If you were training locally, then you might choose the download the zip file and then run the model locally. But for now, we want to show the download code. And then just copy this and make sure you're on Jupyter or Google Colab is the same. And then just copy all of this code. Okay. So now I'll send you guys the Google Colab that I've prepared so that we can test. I'll send over the Telegram group and also the WhatsApp group.
Excuse me?
Okay. So once you open the file that I've sent, the Google Colab file, you'll find something like this. So this is where you paste the code that you just copied. So replace this, the one that I have, with the code that you copied. Oh, not this one. Okay. Okay. Also, in case you do not have your data set, I'll show you the RoboFlow universe. It's called RoboFlow universe. So your RoboFlow universe basically is a free collection or library of data sets that other users have already prepared. I'll show you. I think it's over here. Yeah, RoboFlow universe. So this is the interface. You can search for existing topics. We can also search for sushi, let's say. Okay. And then I will show you. Okay. These are some other projects that other users have done, and they've already labeled their sushis and so on. So you can take some of the images that they already have, or you can just take their data sets entirely. If you go to their project, you can go to dataset and then do the same steps to download or get the code for this dataset. Just make sure that it's the same type that is using also classification, not like object detection or something else, if you want to try. Okay. So let's go back to the Google Colab interface. So after you've pasted your own data set here, you can run the code. This will fetch the data set, and then you can find it locally inside the Google Colab folders. You you will find it downloaded. So for example, this is Sushi Nasilma 1. For me. Okay. After this runs, just make sure you can press on this files on the files icon and make sure that you have the data set for it. So we'll find test, train, and validation, the same split that we previously specified on RoboFlow. Next, we'll also install PyTorch. So we'll be using PyTorch for today's hands-on session. Let me zoom in so you can see that. Okay. Next, we'll just run the import for all of the libraries. So we're importing Torch, which is just the library itself. And then we're also importing the neural network module. We're importing the optimizers. Okay. All of this is the Torch stuff. And then we have NumPy, and then Matplotlib, just for the visualization. OS, just to access the dataset from the local OS. Random, just to randomize some stuff. There is a seed here in case you want to influence the randomization or keep the randomization the same, but it doesn't matter. So just run this block. Okay. If it says running on CPU, then you might need to change the runtime. So you can press on this small arrow and then change runtime type and select the GPU. So it will prompt you to disconnect and delete the runtime, which is okay. Switch to the GPU. Because we're training images, you most likely need the GPU. But once you switch, you have to run back the code from the beginning because everything was deleted. This time it should say GPU when you run this. Is everyone following? Is it okay? No questions so far?
Excuse me?
Okay, so now running on device, it says CUDA 0, which is the first GPU, which is okay. So the first thing that we need to do, now that we have the images from the dataset, we have to, okay, these are the mean and standard deviation values. You can set these manually, or you can just select any random values for now. This is just for the normalization later. So we want to make sure that all of the images are the same size. So I know that we already made sure from the RoboFlow side, but if you're using a custom dataset from somewhere else, where you then select the size of the images, you need to make sure to resize the images to a certain size. So we define this transform, which first resizes the image, converts it to a tensor, which is the format for PyTorch, and then also normalizes these images using the mean and standard deviation. So now the pixel values are normalized throughout all of the images for the whole data set. Okay. So first we'll try to get the trained data set from the training folder. So what this does is, first of all, make sure that this matches the name of your data set. If you go to the folder here, make sure that this path is the same. For example, this is different here. So just copy this path and then paste it over here. So this is the path to your dataset that you just downloaded using RoboCon. And then what this does is just combines this data root and then put the train folder, which or should already exist. If you go inside here, should be the training folder. And then you also have the testing folder. Okay. First thing, we need to make sure that you're using the correct data set. So this will print out the labels. Someone is asking online, how do you get this code? I've sent it through the Telegram and also the WhatsApp, the previous session. Okay. So usually when you're dealing with images, you need to define batch size. You don't usually pass the whole data set at once because this will be very heavy computationally. If you're dealing with numerical data, you can pass the whole data set into one batch, but usually you want to separate the images into batches. So in this case, we're processing 32 images at the same time. And then we're using this data loader to pass the training data set first in order to divide it into the batches that we want, which is 32 images per batch. And then this just returns this data loader, train loader, and test loader. So for training, of course, we'll use the train loader. Then for testing, we'll use the test loader. So you can run this and check that the class mapping is correct. So you have, for this example, should be Nasilama and Sushi. You can also see the number of images, for example, in this case, 61 training images, 8 testing images, and so on. Depends on the data that you collected. Okay. Okay, this is the most important part. This is the CNN network itself. Okay. So this is the same as before. We're defining a network, calling it simple CNN. It's a class, usually in PyTorch. You use classes to define models. And then we're passing a dot module, which is just the PyTorch module for loading models. Okay. We have one argument, which is the number of classes. If you already know the number of classes, you can just remove this argument and just input directly into the model. But in this case, just we're defining the number of classes. And then we have the features. So this is the feature extraction part. As we discussed last time, NN.sequential just means that all of the layers that we define here will be run in order from the first one to the last one. Okay, first layer that we have is the convolutional layer. And then you have some options. The first is the number of input channels. For this case, it's 3, because we have an RGB image. And then the output channels. So the output channels, you can set the output channels depending on the kernel size, or you can just set it to the size that you want. In this case, we just set to 32. The most important part is that whatever value you put here at the output, you need to put at the input of the next one, the next layer. This is the consideration that you need to have. And then you define the kernel size. In this case, we're defining 3. So 3 by 3, the kernel that we're passing through the image is 3 by 3. And then the padding is 1. So we added 1 for the padding to retain the same size. So the input image will be 3 by 64 by 64 because we resized to 64. 3 is for the RGB. And then the output would be 32 by 32 by 32, okay, which is here. So you can also use the equation that we defined previously and then input the size, which is 64, the image size, the number of kernels, and so on, the padding, and then see if you get the same output. Okay. So this output channel is basically the number of filters that you have. So we define the kernel size to be 3 by 3, and then the output channels is the number of filters that you have, the number of filters that you want to use. So this is why this determines the depth, which is the first value here, 32. Okay. And then we run something called batch normalization. This is not really required, but this is just a nice step. It just normalizes also the pixel values, same as we did previously, but now across all the images in this batch. It's good to keep normalizing after each convolution to make sure that they're all at the same scale. But this is really optional. You don't have to make this. And then previously, we also discussed using ReLU after each convolution. So we're just using ReLU. And then we're defining max pooling. So this is max pool 2D. We're defining the pooling kernel size and also the strike. Okay. So after all of this, after the convolution and also the max pooling, the output is 32 by 32 by 32. Okay. I think if you calculate the size at here, directly after the convolution, I think it will be 32 by 64 by 64. But then after the max pooling, it becomes 32 by 32 by 32. Over 50. Same, we have the same exact block here, also here. So three feature processing blocks, each have the same. The only thing that you need to consider is the output size of one should be the input of the next, and so on. Okay. So all of this is the feature extraction part. And then you have the normal classifier at the end. But before we do the classification, you need to flatten the convolution. So if you've seen during the slides, the convolution, the output of the convolution is sort of like a box, a 3D object, which has depth, width, and length. But usually when dealing with linear networks, you just want one-dimensional arrays. So what you need to do is flatten this box to be like a single array. So you do this by, first you need to calculate the number of pixels that you have after the final feature extraction step. So this feature extraction step, the output was 1 to 8 multiply 8 multiply. So this is the number of pixels or the number of features that we have in one array in the next one, which is 8,190. Okay. So now we can define a linear. So this is the linear network. And then the input size for this would be the flattened size that we calculated, which is 8,192. There's also a dropout layer here. So a dropout basically means that it disables some of the nodes during the training, so that no node is fully dependent on another node. Let's say during the training, one node outputs the correct output. The node right next to it is not really doing much, outputting 0. So if you disable this output, the node that has the correct output, you are forcing the node that was not doing anything to now produce the correct output, because it will increase the loss. Suddenly the loss will spike due to this dropout. And then the gradient will have to solve the issue with this node instead of relying on the node that was already there. So this just makes sure that all of the nodes in the network have the correct value, the correct representation of the data set, and also prevents overfitting to the data set. And then after this linear network, your loop is good, activation functions as usual. Another dropout, and then finally another linear network where the output now is the number of classes that we have. In this case, it will be 2, since we have sushi and nasi-lemak. Okay. So our forward propagation is a bit more complex compared to last time, but it's just 3 lines. Last time it was just 1 line where you pass the input to the model. This time we're passing to the features first. We get the features from the convolutional networks, and then we flatten these into one-dimensional array. And then we pass this flattened output to the classifier, which is the final part. Okay. Any questions about this before we move on to the next? Either online or physical. Okay, should be clear. This complete. So the rest is very clear and also similar to what we did previously. We're just training the model. We're running through multiple epochs. And then for each epoch, we're getting data from the train loader that we defined before. And then these inputs we're converting to the GPU because we want to train on the GPU. And then we run it through the model. We get the outputs, calculate the loss, and then run the optimizer to fix the nodes using these losses. And then that's all. Repeat this process for a lot of epochs until the model learns the behavior. So now we can go ahead and run the training. If everything is working so far, the training should start, and you can see a screen like this where you can track the loss. You can increase the number of epochs if you see that the training is not reaching a very low value for loss or very high accuracy, like this case, 100%. But this is because our data set is very small. Usually, this is a red flag. You don't want, like, if you're training on 20,000 images and you get 100%, then something is wrong. Maybe you don't have enough test images. Maybe the split is like one test image and 99,000 train images or something. It should be like 99, 98, 97. These values are realistic, but 100% is, means usually something is wrong. 50% means a lot of things are wrong. So try to train and let me know if you have any problems. Try to use your own dataset that you just labeled. But if it's not complete yet or you're still having trouble labeling, you can use just one of the available datasets at the RoboCon universe. Just pick an object and then train using this object. But make sure that the type is classification. So you can select by project type here. Make sure to select classification because the model that we have is a classifier, not an object detection model. Here you can see some of, I think some of you guys or someone else. Because it's named sushi and then the image is nestled. Probably one of you guys. I'll give you around 5 minutes to train the model or run the code of the training part. And if there are any issues, let me know. Okay. Has everyone trained their models? Do you have a nice accuracy percentage, or is it very low? As long as it's like above 50%, should be okay. Because this is a very simple model. It's not the best model for classification. We just made this using like a very simple three-layer, three-block convolution networks. So there are more advanced architectures. So let's see the architectures that are currently available, or let's start historically first, and then go to the most recent ones. Okay. So there's this challenge that was conducted called the ImageNet Challenge. Basically, the organizers of this challenge, they provided a huge data set that has more than 1,000 classes and has around 1,280,000 training images and like 50,000 validation, 100,000 test images, a very huge data set. And this was even before they used convolutional neural networks. It started in 2010. And the challenge was simple, just make the best model using these images, this data set. And this data set was available on Kaggle. Okay. So it was conducted every year, and you can see the error or the classification error drop every year that they hosted the competition. And at the beginning, they were just using normal like neural networks, feature engineering. And then starting from 2012, they started using convolutional neural networks. And even with that convolutional neural networks, the error varied. Every year it was dropping, depending on the architecture of the model itself. So usually the difficult part is to come up with the architecture of the model. So let's go through some of the most prominent examples from the participants in this competition, because they also were iconic models or architectures for image processing. So the first one that we have is AlexNet. Okay, this guy called Alex, and then a Russian name that I cannot pronounce, Chris Fish something. Okay, he was from University of Toronto. He's the winner for 2012. So this is the year that they started to use convolutional neural networks. Okay, and his model was relatively simple compared to today, but still a bit more complicated than our model that we just developed. So it had 5 convolutional layers, some of which had max pooling, some of which did not. And then it had 3 fully connected layers at the end, which is the classification part. Okay. He used a ReLU, very simple. And then, he used ReLU instead of sigmoid or 10H function. And back then they were using a lot of sigmoid and 10H functions. So this already increased the performance, made it 5 times faster. He used dropout to prevent overfitting, which increased the training time, but also meant that his model does not have much overfitting, so it can deal with a lot of variation in the images. And the model in total had 6 million parameters. Okay, these are the weights that are trained in the model itself. So this is the architecture that he had for the model. This is the AlexNet architecture. This looks a bit more complicated, but basically it's the same So these are the 5 convolutional layers, starting from this one. This is the second, third, fourth, and fifth. And then these are the 3 fully connected layers, or the normal linear networks. It looks complicated, but it can be drawn much more simply. This is just a complicated drawing for no reason. Okay. Okay, next we have this VGGNet in 2014. Stands for Visual Geometry Group, and it was from University of Oxford. They were not the champion, they were not the winner, they were the first runner-up, but still was much better than AlexNet from the previous year, or 2 years. It had 16 to 19 layers. So AlexNet, if you remember just now, had 5 convolutional layers and 3 fully connected layers, so 8 in total. This one had 16 to 19 layers. And then 13 or 16 of them were convolutional layers, and then 3 fully connected layers, followed by softmax activation function. Yeah, and then all the hidden layers had ReLU activation functions. So this is the VGGNet, already much bigger than the model that we have today. The CNN model that we developed was just 3 convolutional blocks and then 2 fully connected layers. So this is much bigger. And then this is the architecture. So it is convolution 1, convolution 2, max pooling, convolution 2, and so on. So many convolutions. And then at the end, fully connected layers for the classification, of course. Nice. But the actual winner, the actual champion, was GoogleNet this year, 2014. It was designed by this guy, Christian Gidi something. And then it was codenamed Inception. It had up to 22 layers, so already more than the VGGNet. They just keep increasing the layers. And the unique feature that it has is 1-by-1 convolution. So this was new at the time, this 1-by-1 convolution. I'll explain after this. And also introduces something called the Inception module. Also used global average pooling, which is another type of pooling, different than max pooling. Basically using the average, the global average, to take the. So instead of just picking the maximum value of this matrix, it calculates the average of this matrix. Overall, it only had 4 million parameters. For comparison, AlexNet just now in 2012 had 60 million parameters. So this had more layers, but less parameters because it was using this 1-by-1 convolution, which I'll explain in a while. And also the accuracy, the performance was higher. So it's not necessary to keep increasing the computation and the number of parameters to achieve higher performance. So this is the architecture of GoogleNet. We have some convolutional layers, C1, then this is pooling, P1, C2, C3, C4, all convolutional layers, and then P2, another max pooling layer. And then this is the Inception module that they describe, which also includes the 1-by-1 convolution that they also describe. And then they just flatten the output and pass it to fully connected layers, and they get the output. Okay. So let's explain a bit what they did. So first of all, this 1-by-1 convolution. So this is achieved by reducing the number of channels and the 3D volume. So what they want is to take one pixel value, one raw pixel value, just like this, and then perform the convolution lengthwise so that they obtain like 1 pixel. Okay. So this is much more efficient than running the convolution as a kernel and then passing it by the whole image. So this is a lot of computation. But if you just take one pixel, including the depth, like this, and then run the convolution to obtain one pixel, there's a lot of dimensionality reduction. You started with this huge 3D object, which is the number of the depth is the number of filters that it has been through, and then the width and the height. and then you condense all of this into like a flat image, kind of, because the depth disappeared, because we're running it depth twice like this. So this is much more efficient than the other convolution. Okay. And then they run, instead of using, yeah, it already is non-linear. Okay. Nice. So this is how you can afford to have so many layers, but still maintain less parameters and also less computation compared to AlexNet. Okay. This is also the inception module. So there are different versions of this inception module. Overall, what it does is it is used in combination with the one-by-one convolution. It also, yeah, 3x3 is too expensive, hence 1/1 is number of convolutions. Yeah. So in the naive version, which is the one that they used, which is this one, they used one-by-one convolution. And then you have this inception module that uses normal convolution, 3x3 and so on, and also has one-by-one convolutions. So it depends on the number. So overall, you just have the start. You run the same input through different convolution operations or pooling operations, and then you return them all. You combine them back all into one. This is basically the inception module. It's just a way of arranging the layers so that it's arranged like this. You have a starting point, goes into different operations, and then returns back to the ending point where they're all combined back again. Okay. And then you have this global average pooling. Okay. It just, as I said, gets the average value and then combines them to get the pixel value. It's just a pooling technique, different from the max pooling technique that was used before. Okay. You don't have to really understand all of this. This is what they used back in 2014, so it might not even be relevant at this point. Okay. You should look at the newest operations. Okay, then finally we have ResNet. This was in 2015. So this was proposed by this guy, Ismail, and it has up to 152 layers. So we jumped from 22 layers in 2014 with GoogleNet to 152 layers with ResNet, and also introduces this deep residual learning framework. So it uses this residual learning. Basically means that not all inputs are passed in order like this. Some of the inputs are skipped to the next, for example, to this, added to this loop, and then continued. Okay. So these shortcut connections, they call shortcut connections, will just add the input of X to the output after a few wait layers. This shortcut. So this reduces some of the computational complexity because some of the inputs are not processed through all the network. So this is the ResNet architecture. It barely fits in the slide, but you can see all of the skips, all of the shortcuts that they have. These shortcuts. In total, 152 layers. Okay, so now, just now we use the data set that we have, but we use the simple CNN network that we defined. So now I want you to use AlexNet to train the same data set that you had previously, and then see how the performance of how the accuracy increases. So I'll send you the Google Lab link, and then you can test. Okay. So you should have received this code, AlexNet classification. So all you have to do is also copy your data set, put it here. And then don't forget to change the path also to your data set. This one, the data root. And then you can run everything and see if the performance is better than last time or not. So you can see that here we also manually define the AlexNet, just that we follow the definition that is known for AlexNet, which is 5 convolutional layers. So that's layer 1, layer 2, layer 3, layer 4, layer 5. And then you have 3 fully connected networks, FC, FC1, FC2. The last one has the number of classes. So this is the same as the AlexNet that we described just now. And then the forward is just passing all of these layers, reshaping to flatten, and then, yeah, just the output. Let me make sure that you do not have edit track. Make sure to copy this, not just edit the one that's here. Create your own copy. Okay. Let me know how much the accuracy improves from the normal CNN that we just used. Okay. Did you guys see? Did you notice the accuracy change? If you're training with a few images, you might not see much of a difference because probably you were already at 100% at the beginning. But if you increase it, nice. It should increase because this architecture is more uh, powerful than the one that we defined at the beginning. Okay. Do you have any questions so far? I think we can take a short break. And also, if you're Muslim, you can pray the prayer. And then let's continue at maybe 4:30. Or let's make it 4:35. Okay, take some time. The last thing that we have is transfer learning, and then we should be done. let's continue, even though some people are not back yet. Okay. So the next topic is transfer learning. So the idea behind transfer learning is each time the model is trained on a data set, it will also learn some general stuff that can be generalized to other data sets. Okay. So the benefits include that learning itself can be faster for the new data set. So basically what you do is that you train the model, or you have a model that is already trained on a previous data set. Okay, let's say in this example, task A is to classify animals. Okay, and then you have task B, which is to classify X-ray scans, which is different, of course. But then there are some general aspects that might be generalized between these two that allows the model that has been trained already to classify animals to become better at classifying X-ray scans, basically. So the learning process itself can be faster because the model is already trained on. I mean, if the task is similar, in this case, classifying animals and X-ray scans are not very similar. But let's say you had a model trained on all animals, for example, and then you're trying to detect zebras. So if you start with a model that already has the knowledge on how to classify all of these animals, and it's called fine-tuning, fine-tune it to just detect zebras, it's going to be faster than a model that's not trained before and then suddenly now is trying to detect zebras. Okay. And of course, it requires less training data because the model already had training data before. And now you only need to include the training data that it has not seen before in order to fine-tune this model. Okay. So this works better when the tasks are nearer than this example. So in this example, classify animals, and then you want to classify X-rays as the second task. So you have a model that already classifies animals, and then now you want to use it to classify X-rays. The transfer will not be that much. There's not much in common between animals and X-rays. But if you have a model that is really trained on animals, for example, and you want to train it to detect zebras, then it makes sense. Then the training would be faster, and then the results would be better. And you can also use less training data for this. Okay. So basically what happens is, as I mentioned before, you have a pre-trained model, and then because it already has seen a lot of data or relevant data to the task that you want to do, it can be transferred, this knowledge can be transferred to another model. So it's not actually transferred, we're not like taking the data from the previous model and putting it in the other model. We're just retraining the same model that has been trained previously, but then using a different data set for this model. Okay. So it already has all the weights from its previous training, and we're just adjusting these weights slightly for the new task. So it already starts closer to the end goal than if you were training a model from scratch. So there are different ways that you can do this. You can either train the whole model again, or you can freeze some parts of the model or some layers of the model and then allow some others to be fine-tuned. So these are called frozen layers. We don't want to change these frozen layers. And we can keep some of the layers, usually towards the end, the last layers that we want them fine-tuned. And how much we freeze or leave to fine-tune depends on how different the task is from the initial task. So let's say our initial task in this example is X-ray scans. Okay. And then we want to do a radiology diagnosis. So since these are similar already, you might only need to fine-tune the last layer, which is the classification layer. Okay. But if, let's say, okay, this is also the same, but let's say you have a different task at the end here. Instead of radiology diagnosis, I don't know, disease diagnosis for bacteria or something. Okay, so it's slightly different. It's not really the same as radiology and X-rays. So you need to fine-tune more layers and then keep less layers frozen. Okay. So how many layers to freeze, as I've discussed, depends on how close the source domain and the target domain are. So if they're similar, then you can freeze more layers and then fine-tune only the classification layers. If they're different, and then you might need to fine-tune more layers. It also depends on the labels. So if you only have a few labels at the end, at the target task that you want to do, you can still freeze more layers or freeze most of the network. But if you have suddenly so many, let's say the source task only had 2 labels or 2 classes, and then the target task has much more labels or tasks, then you probably need to change more, fine-tune more of the layers, and then freeze only at the beginning, maybe. Or just fine-tune the whole network. You will still get the benefit that the weights already start somewhere closer to the classes that you already have compared to network that starts from scratch and has not seen any data before, and it's all random weights. Okay, so now we have a hands-on session, our last hands-on session for today. And in this session, I'll give you the AlexNet network, and it's already been trained on the ImageNet classes. So all the 1,000 classes, the 1,200,000 something images. And all you have to do is fine-tune this network to use for your data set. And then you can compare this fine-tuned network that was already trained on ImageNet. Is it better than the AlexNet that was from scratch, that we trained from scratch last time? See the difference in accuracy. The transfer learning actually improves the performance of the model, since they're both the exact same architecture. One has been trained before and one we started from scratch. And let's see which one has the higher performance. So I'll send you now the notebook for this. Okay. You should have received the notebook, the Google Lab notebook. Let's take a look. So the only difference would be in the part where we define the model. This time we're loading the models from the internet. We're just loading the AlexNet network and also loading the weights from ImageNet. So these are the weights, ImageNet 1K V1. The model is AlexNet weights from ImageNet. So this model has already been trained. So now this is the freezing part. So how you do freezing in PyTorch is basically saying to the model that this layer does not require any modification when you're doing the backward propagation. So you can do this by setting this flag requires grad. Grad is the gradient when you're calculating the backward propagation. So you set it to false. So this means that this will not be modified during the backward propagation when the model is learning. So that's all you have to do to freeze some of the layers. So you can see that the model already has a subclass called features, which includes the convolutional layers. So what we're doing here is getting the length of this. You will print out here when you're in the book. And then we're freezing the first 5 layers, basically from 0 to 5. We're freezing these layers. And then the other layers we're allowing to get fine-tuned. Okay. We're also defining our own classifier depending on the classes that we have. So we only have 2 classes, right? The sushi and nasi. So we're creating a new classifier. First, we need to remove the classifier that was already here. And then we need to add our own classifier at the end with the number of classes that we have. So we need to find out the features, the input features of this one that we're replacing. And once we know these, the length or the size of the input features, we can use it as the input to our linear network. the one that we just created at the end there. So the model already had this model classifier 6. This was already the classification layer at the original AlexNet network. So we want to know the input features. What was the input size for this classifier? And then we take these input features and then we use them in our own linear network that we created now and end up linear. And then the output would be the number of classes that we want, which in this case is 2 classes for the sushi and the nasi lemak. Okay, that's all. Now run the rest, should be the same. And then let me know if it has higher accuracy than the one where we trained AlexNet from scratch. Okay, so is everyone already have the trained model? Yes. Is the accuracy higher than last time? Yeah. As usual. Okay. So the idea is, as I said, when you have a model that's already trained on some images, and then you train it or you fine tune it on another task or the classes that you want to use, usually the performance is better than a model that is trained from scratch. So it's always more efficient to start from a model that already exists, if you have a model that already exists, and then fine tune it or change the classes that it has at the end, train it on your own data set. So it's as if you added your own data set to the existing large data set that the model was trained on at the beginning. Okay. So I think that's all for today's session overall. So at the beginning, we described CNNs. I told you what convolution is, the operation of convolution, pooling, and so on. We explored writing our own CNN from scratch, and then we went through the ImageNet challenge, where we've seen the progress of networks over the entire period from 2010 until we stopped at 2015. But of course, the competition is still running, and they're developing new models every year. And then finally, we explored transfer learning a bit. So now, if you plan to continue, if you like this image processing route using CNNs or transfer learning, you can also explore object detection. So today, all of the tasks that we had were classification tasks, where you just classify the whole image. You can also explore object detection tasks, where you also draw a bounding box over the thing. Usually, they use the YOLO model, but you can explore what is the architecture of the YOLO model itself and how they process the data to not only output the image, but also the numerical values for the bounding box and so on. So you can explore this on your own time. So if you have any questions, I can answer. I think this is now the Q&A session. And also the same for the people online, if you have any questions. If not, then we can end this session. Any questions overall? Okay.
Yes, sir.
Mm.
How do it? How do it? Because they have problems, and it's possible.
Oh. If you have an imbalanced data set, that usually means that you have a lot of images for one class and then not as many images for another class and so on. So usually, if you can take more images for the class that is missing some images, you can take more images. Usually, you want them to be equal. You want all of the classes to have the same number of images. So if you're training for 5 classes, each, for example, 500 images, so that you have a balanced model. But if you don't have this, you can either remove images until they're the same number, or you can add images from the classes that are missing images so that they're all balanced. And usually when you're trying to take a data set, you want to take images from the camera that you will be using for the detection later. If you're using it on a robot or something, if you're developing a robot, then use the same webcam that will be on the robot to take the images for the training. And then try to have some variety. So you can put the object that you're trying to detect far away from the robot, close to the robot, in different brightnesses and so on. The more the model sees, the more that it will be able to detect at these different conditions. If it only sees like the box at a specific distance and a specific light, then it will overfit to this. It will only think that this object has to be in this lighting, has to be in this position that you can be. So to prevent this overfitting, you need to take images from a variety of positions, variety of lightings, and so on. Okay. Any more questions?
Will you say when on a system, for example, on level, like and when you say you says I want to get I think it's even better.
Yeah.
You said that I'm going to just make an option or I'm going to use the arm.
Okay. Usually you want to use the ones that already exist. Usually you're looking for the state of the art, the best model when you're starting a new task. You want to select the best model and then select the model that has been trained on data similar to your task. So you always want to start with the model that has the most information about the task that you're trying to do. So if you're trying to develop a model to detect bend, for example, then you look online for example, the YOLO model that is trained already on using detecting the bends. And then you just add to this data set, you add some images of your own on the bend that you already have, and then you train the model. Or you fine tune it. You don't have to get the data set that they have. You just need to get the model weights that they have and then train it on your own data. Usually you want to use established models like YOLO or ResNet and so on, because usually they've gone through years of development to achieve this performance. Unless you're doing research and you want to create your own, then you have to find your own contribution and create your network.
How will one side lecture for all and also create
I think you can start studying. You can load any model into PyTorch, and then you can print out all the layers for this model, including YOLO and so on. So you can find out what is the architecture that we use. I recommend reading papers. You can read most of the models already have papers published explaining everything, the experiments that they did, and then the architecture of the model if you want a more in-depth understanding. And then once you feel like you have some understanding of this model, you can start by modifying the existing models. So let's say AlexNet, the one that we tried now, you can try adding more convolutional layers, changing the position of the pooling maybe after the second layer instead of at the end and so on. And then you might get better performance, and then that is already a contribution. Any other questions? Maybe from online, if you guys have any questions. I'll share the resource to them. Okay, sure. I'll share the slides that we had for today. And you already have the hands-on session codes for the Google Lab. If I find any interesting papers, maybe on AlexNet, maybe I'll share the AlexNet research paper on the group. I can find it. Most are written in Python. Some will try to improve the running like computational cost by converting to C++ because it's faster. But this is only for like optimization cases where you have to run on limited hardware and so on. But most of the time, 90% of the time, they use Python. Some people use R, programming language R, also for some data science and running models and so on. But most of the time, it's Python, either PyTorch or TensorFlow. Okay. Any other questions? Okay, someone is asking, among many available courses, I myself get lost which one to start? Okay. I think, like I said last time, usually it's better to just directly go into projects. You don't need to get stuck watching a YouTube video for 5 hours explaining the syntax of PyTorch. It's usually useless. All you have to do is pick a project that you want to do, and then you will learn much more by doing this project than by like, following someone on YouTube explaining the syntax. And you will memorize it for much longer. Usually when you're watching like a YouTube video, the syntax, you forget. The next day, you probably forget. But if you're trying to do a project and then you're stuck somewhere or you need the syntax and then you look it up on Google, then you will remember this for a very long time. Okay. I think that's all. Maybe we should take a group photo. Yeah, let's take a photo. Oh, okay. Okay. Now you can tell us.
Okay, hi guys. So thank you so much for joining this session. So I would like to request that you come to the group so we can have a coffee. And for those joining online, we'll have a response for you. If you like in front of the request. Please sit in the middle.